Well, we made it, folks. Welcome back, everyone. Week two is officially last class, about ready to get going. And even though this was a holiday week, it feels like we put in a lot of work this week already. Just meeting Wednesday, Thursday back to back feels like a lot of effort. But we'll get used to this as it goes on. Week three, we're going to see what a just normal class looks like, where we're working every day. We have a quiz in the end. It's pretty much going to be a redo of everything you see here, from module to module, which are just the weeks numbered. It'll be like a record of all the things we do. The new thing we've got going on this week is first quiz is being posted, quiz number one. They're all going to be normalized to 10 points. And I mentioned they're really kind of a participation credit. They're not a quiz in the traditional sense. So they're a take-home quiz. I'm not going to ask you to take out a sheet of paper and solve it right here, right now. And the due date is always going to be a week away from when it's posted. So this one's due September 11th. So first thing we have to do is just open this up, see what it looks like. It's really pretty basic. Just click on the quiz one link right here. And it just takes you to a PDF. And the only reason I write it in as a actual quiz structure is just because it puts in a due date. And sometimes that's just a nice thing to see on Canvas. Otherwise, I might have just posted a PDF that just said quiz one, and that would have been the same kind of effect. So because of the due date, it's something you have to click on basically twice, sort of annoying. And then it opens it up like this. You can download it if you like. It's just going to be a PDF document. What this looks like is maybe like a problem right out of the notes, something that we've solved pretty similar. This also looks like what an actual exam question could be. And that's going to be my sort of format for writing out these quizzes. We mentioned it's kind of an effort of bridging the gap. Sometimes the problems on MyLab statistics just feel a lot different than what a real question would come at you as in an exam setting. So this is my attempt to show you what a real exam question is going to look like. But again, it's oftentimes pretty similar to the actual lecture notes. My lecture notes are also meant to be pretty similar to real exam questions. Sometimes it's just kind of a do-over of what I think to be an important concept question or important computation. Turns out quiz one is pretty similar to example one in section 2.1. So there's loads of ways you can solve this quiz. If you're the traditional sort of person, just take out lined notebook paper, spiral notebook paper, something like that. Or something like this printer paper with a blank side on it. And then just solve your quiz. You could just say, put down your name. Part A, this is your answer. Part B, this is your answer, and so on. So if you want to just work in that kind of way, you would just take out some notebook paper, open this up on your laptop or tablet, something like that. Maybe not a cell phone unless it can really have nice resolution. Sometimes it might be hard to see everything on there. And then just turn in on September 11th, before or after class, your quiz, and you're all set. So that's one way to do it. Yeah. Yeah, absolutely. That'd be a great way to do it as well. Some people like when they get their quizzes back, they want to know what the question was, what all the parts are, that kind of thing. So if you're that sort of person, yeah, you're welcome to print these out. Just solve it directly on paper. That's why I have the spacing there. It'll give you a feel for what real spacing looks like on an exam question as well. And then I'll accept your paper. I always give good feedback on your exams. So I'll just put a check if everything looks great on every part. If there's anything missing, I'll give you feedback so you know when this comes back as a real exam question, the context changes, but the problem is essentially the same. You'll know what you might have missed. So either just take out blank notebook paper, that works out fine, or print it out, that'll work just fine. Or some people might want to download it and then use digital tools like this to start marking up and so on. Imagine that's an answer or something like that. So if you've been working digitally in this class and you want to just keep on doing that, that works out fine as well. What you would need to do is just save this as a PDF, send it to my ISU email, and I can accept your quizzes by email as well. That'll always be totally fine. If you ever found yourself in a situation that you did quiz one, but maybe you just couldn't make it to Thursday's class, you can just take a cell phone picture of it or put it under a scanner, send me the file, and I can accept it that way as well. So everyone's got a lot of ways that they might be doing this. I think we discussed 3 different ways. You have a lot of ways to turn it in. If you give me a hard copy, I'll return your hard copy on the next Tuesday's class when I see you at the soonest. If you send me a digital file, I'll mark up your digital file, kind of like what I'm doing on these notes, like up here, and just email it right back to you. So that's how each one of these quizzes will go. Any questions at all, folks, about turning in or doing the quizzes? Okay. And let me just emphasize what I said earlier, but never came back to. I mentioned that even though they're called quizzes, I'm only calling them a quiz because we have homework in my stats lab. So I didn't want to call it homework. Now it's confusing which homework I'm even talking about at that point. This is like a participation credit. It's just your way of participating in the class, getting a feel for exam questions. So this is essentially open. It's a take-home quiz. You all can work in groups. You can collaborate before, after class. That's totally fine. You can ask me direct questions about this quiz, and I'm happy to help out. It's only meant to support you. So the quiz credit is not meant to be anything major in that kind of sense. It's harder than the MyLab statistics because once you do turn it in, there's no change in your answer after that. So it does get finalized. And a comment I think I might have said in class on the first day, we said a lot of things on the first day, was because it's a participation credit, all of them are 10 points, and you get 5 points just for turning it in with your name on it. You've participated in some way. So even if everything's wrong, I'll give you a lot of feedback to help you out. You got 5 points out of 10. If you made some simple mistakes, you might lose a point here or two. But in this class, because it's a participation credit, people tend to do really well in the quizzes. We're also going to drop the last two. So if there's two, you just maybe got 2 5s and you felt really bad about that, really doesn't start hurting your grade unless you start losing on several more quizzes, a lot of points. If that's happening, just reach out to me. I'll be happy to help out with your next quizzes so that you're doing better on the next ones. So that's how all of our quizzes will go. Any questions about them whatsoever? Okay, so the due date is generous because again, it's open to questions, it's open to class collaborations. Just ensure you're writing your own answers, and then that's the only major requirement there. So a 1 week turnaround gives you that extra time. But honestly, the best time to do a quiz is as soon as possible because all this information you put in your head, it has a real shelf life. It starts to deteriorate. The soonest opportunity to work on that quiz is when you're going to solidify the knowledge the very fastest. That's when the quizzes is at its easiest. I know we're a night class, so I'm not saying when class ends, do your quiz right away. That's not realistic for us. But at your earliest convenience, it might not even be tomorrow morning, it might be after work tomorrow. The sooner you start working on it, the easier it'll be. And it also means the sooner you might have the opportunity to ask a question if you needed additional help. So that's my spiel on quizzes. We'll post all of them at the end of each one of these weeks. So our next quiz will be always at the very, very bottom. I might sometimes post it on Wednesday if I'm working ahead, but it's just always going to be officially posted on Thursday with a 1 week turnaround. So they're meant to be short and sweet, just one problem, sometimes with multiple parts, but if there's like 5 or 4 parts like this one, they go pretty rapidly. It's not meant to take too much time because of the additional homework and the MyLab statistics as well. So I have to balance that at the same time. And aside from that, I think I'm running out of my major announcements. Other thing I did want to talk about is our first due date is approaching. And so that means I'm going to start getting into a habit of on the weekend, on Friday if I'm caught up, but maybe as late as Sunday if I'm working a little behind, getting everything in line. I'll be pulling your grades out of the MyLab statistics homework and uploading your results here under grades. So everyone's grade, unless you join the class late, it might be blank, but everyone's grade should be already 100, you might have noticed. And now I'm going to start pulling in information on where how you're doing in the class. So on a weekly basis, get in the habit of checking this. Your grade will change on a weekly basis. Again, sometimes on a Sunday if I'm a little bit behind, but always when you come back to class on Monday, it'll be refreshed and updated. Right now, it's going to be purely based on MyLab statistics. So if you're a little bit behind, the grade might not look pretty, but if you miss this due date, you can still get back in there, make up the work for full credit. So keep on checking your grades. I'll be posting your grade results and all that kind of stuff. And this is good advice for any one of your classes. Keep an eye on that target. And if your instructor isn't posting grades, just send them an email. They should be keeping you up to date one way, some way, somehow. So that was my big set of announcements for class today. Any last questions or comments before we get started? Okay, let's get started then. So we are in section 2.2. We're handling quantitative data now this time. We left off on, well, we finished off this problem right here. Our whole job was to take a lot of information, a bunch of information about number of crimes reported, and just visualize what's going on with the data. We mentioned the extreme outliers, the centralized value where everything seems to be aggregating or accumulating. And now, for example, two, like we mentioned, a common graph that we're going to see a lot is now the histogram, like on this one. So here's our first real look at a histogram. Some folks have mentioned they've seen them before. If that's you, then that's awesome. If you've never seen anything like this before, it's something to get used to at the moment, but it won't be too bad. First, this was real data, so let's carefully read through the context, see what's going on. It says the accompanying data, just in the form of the histogram, so I don't have the raw values, but the accompanying data was reported in the article, synovial fluid pH, lactate, oxygen, and carbon dioxide partial pressure, this is heavy stuff, in various joint diseases. We're not experts at all at any of this. This is the Arthritis and Rheumatism Journal, old data from 1971, but still interesting. You can look this up if you'd like. What's cool about statistics is you don't have to be an expert here. We can still talk about the data, even if we're outsiders looking into a really very specific discipline. Rheumatoid arthritis is one of those not nice diseases where your joints, your immune system attacks them, and they sometimes swell up. Imagine this is your knee joint. It can swell up, and sometimes they have to do what's called a joint aspiration, where a needle goes into the joint space and pulls out some of that fluid, that so-called synovial fluid, to relieve the pressure and the pain there. So that was a pretty common procedure, and it still is to this day. And they were looking at this fluid, studying it to try to help these patients better. They were wondering how acidic it is and various other factors that I don't know too much about. So that's what's going on in the study. And we're told the observations are pH values. So that's the one variable we're focusing on this time, of the joint fluid, synovial fluid, which lubricates the joints and tendons, taken from the knees. That's a common point of trouble for rheumatoid arthritis, of individuals suffering from just says arthritis. So here's a histogram of the data. Let's look at this carefully. There's one variable here, and that variable was pH. So this is our quantitative variable. And once we have the quantitative variable, we just list it on the horizontal axis. At this point, not too different from looking at categorical data. Let's just take a quick peek. When we handled categorical data, we had one categorical variable, and on the horizontal axis, we just put down the categories. Well, quantitative variables don't have categories, but what we do have is the number line. These are all numerical values, so we can organize them by their original organizing structure of just the real number line itself this time. And sometimes these graphs look a little bit weird. It's just kind of unfortunate that this edge right here didn't match up with any specific number. It just went 7 to 7.2, up to 7.8, a little bit off the scale here, and a little bit off the scale here going off to the left as well. Let's go into part A right away, because this is going to explain what we're really seeing on this histogram. It asks, how many people in the study had a pH of approximately 7.0? We can't say exactly here, so the word approximate is very helpful. And 7.0 is right here. The categories for 7.0 are what this rectangle is meant to specify. If we're looking at the tall rectangle, this one, it goes from looks like about 7.1 to about maybe 7.25, a little bit further on. It says on this one, if we just highlight this one just for the moment, doesn't answer a question, but it'll help us. Between a pH of about 7.1, just above 7.2, there are 5 individuals of this study with those kinds of values. So that's what the histogram is trying to say. Where are all of our values located at? In fact, if you think about the dot plot, that's all the dot plot is trying to do. And we could have put rectangles around these to really convey these kinds of things. Would have looked like that as a histogram, for example. But if we're doing a histogram by hand, there's a little bit more to that. It takes a little bit more work than just putting the rectangles as we did. But that's just a way to say we weren't doing anything too different. We're just showing where the data was in the dot plot. Same idea down here on the histogram. We have frequency. This is the number of people, individuals, or objects, if they are objects, in the sample. So that's what frequency is saying. pH, this is the quantitative variable. And so once again, this is just saying between 7.1, just above 7.2, 5 people in the sample had that range for pH values. Well, does that make sense to folks so far? What's going on with the histogram? Okay, the question here, let's highlight this one just to get a good read on this histogram. How many people in this study had a pH of approximately 7? Again, that's hard to say because when I look at this, the height is 2. So there's 2 people from just below 7, maybe 6.8 or 6.7, all the way up to 7.1. Let's put that tick number there just for emphasis. So we can't say exactly, but it looks like there's about 2 people in this region, approximately at a pH of 7. So we'll allow that to be closer to about a 7.1 as well, and maybe around, say, a 6.8, 6.9 as well. Let's say here, about 2 people. So part A is just all about saying, what is the histogram trying to tell us? Where does the data actually end up? Any questions, folks, about getting this value, about 2 people? Okay, so that's all that's going on with the histogram. And there's a lot we can say about this. Because the number line has a specific order, 7.0 becomes before 7.2, becomes before 7.4, there's a definite shape that always emerges on our histogram. When it comes to these things, the shape is just the order you decide to go. No one would have stopped you. It would have been weird because the table's order here, but if there was no table and you're just doing this on your own, no one would have stopped you if you made the smallest one come first and then worked your way up. You would change the whole shape that you're looking at. Or Japanese could have gone over here and then American. In other words, a bar chart can have just about any shape that you would like with the heights that were given. So we can change shapes willy-nilly on a bar chart. No one's going to harm us. There's no order here whatsoever. But histograms are different. They have specific shapes. And knowing those shapes is actually really important statistics. Some procedures work for nice symmetric looking shapes, and those same kind of procedures can fail if they get too extreme, if there is too much what we'll call skewness later on, or if there are too much of an extreme outlier. By the way, that's a really important question already on this one. On this data set right here, we call that an extreme outlier because that one observation was just totally away from the main grouping of data. And now here, there is one observation. Let's change the color on this one to orange to not make it look like it is bad. But there is one individual who's just a little bit different. This one, however, is not an outlier, which seems kind of odd, right? It did leave the main grouping of data, which is these four rectangles right here. What's the problem? It's that it just didn't leave it by enough. If it happened to be, say, over here instead, now we're looking at an outlier. It's really got to be actually kind of somewhat far away from where everyone else is for us to really see an outlier. If it happened to be maybe just way over here in this far region, then that starts to look a lot more like what was going up here. Now it's an extreme outlier. It's left the pack totally. It's just going its own way now. This would have been really rough for a pH. So this one, just because there's a little bit of separation, doesn't automatically signify you're looking at an outlier. We're not that punishing. It's got to look really weird, in other words. So by really weird, once again, think of pictures as extreme as this one. That's pretty bizarre. And really weird for quantitative data is something like this. Or like we mentioned, it could have been out here and starts to look pretty weird as well. But if it's over here, maybe a little bit nudged clear to the right of this one, that's not too bad yet. And that's kind of what's going on with this one. It's nudged to the right, but not by much. This is all purely subjective, purely qualitative, so it's kind of hard to say exactly, is it an outlier or not, just by looking at the histogram. So I'll have some extreme ones that we'll be taking a look at later on in the notes. And as we've hinted at before, we're later on going to get formulas as well. But here's a good rule of thumb to help us out. Not an outlier. It should be more than 2 spacings away to be considered an outlier. That's a really rough rule of thumb. And by spacing, I mean there's a space here. No height on a rectangle, so nobody is between about 7.5 and maybe 7.65. So that's just one spacing. If there's more than 2 spacings out, if it's right around here, for example, it starts to look weird. And that's when we start to consider it an outlier. So let's just call this a rule of thumb because that's all it is. But it's a great way to start thinking about it if we want some kind of process when we visualize these. Any questions so far, folks, with the outlier discussion? Okay, still it's an interesting observation. It affects the shape of this overall distribution of data that we're looking at. And part B is asking just the next interesting question. For most subjects, let me fix my controls here first. For most subjects, what is a typical range for the pH of the synovial fluid? This is a slightly tougher question as well. What is a typical range? It's hard to know what we're really saying, but it goes along with what we were saying above. We circled this to say these were the typical or central values of the data set. This is where people tend to be accumulating around. And when we look at a histogram, that's something that's really important to us as well. So when we're talking about what is a typical range, again, there's lots of ways to interpret that. But I would say this is more talking about what are, or let's say it this way, what is the range of the central values is one way to think of that question. So in other words, where's all the data piling on? Any volunteers to give a couple set of numbers that seems to contain just about everybody? Not necessarily everybody. We don't want to say 7.0 to 7.8 because this was slightly atypical, and so are these two kind of observations. We want just kind of a narrower range where we think the average might be contained in, for example. How about 7.1 to maybe right around here? Would that make sense to folks? I'd say it's a pretty good way to answer it. The average has got to be somewhere in the center here. So much like we said, the typical values or the central values seem to be somewhere inside here. That's all that we're trying to say on this problem as well. Again, it's a slightly uncomfortable question, right? Because it's subjective. There might be some other slightly different answers. And if you did say 7.0 to 7.8, well, that is a range that contains everybody. My instructions weren't specific enough. That should have qualified for an answer as well. But the spirit of this question is really going from 7.1 to maybe wherever this tick mark is. Let's just approximate and say the typical values, the typical pH values. It's good to bring in some of the unit just by mentioning that, bring in some of the context by mentioning the unit. It reminds us this was people suffering from rheumatoid arthritis. This was synovial fluid from the knees. And those typical pH values are from 7.1 to, I would call that maybe 7.35 approximately. 7.3 is about here, so maybe that's about 7.35. Not perfect, this is all visual estimation. It's subjective work as well. If this feels weird and uncomfortable to you, it gets better. We're eventually in section 2.4 going to calculate the statistics, the mean or average value and the standard deviation. Here, major thing we're just doing is just trying to get used to this problem, used to looking at histograms and what they're trying to convey. Any questions about the histograms so far? Okay, I guess I have a interesting question for the class. It didn't say it anywhere in this problem what the sample size was. Any volunteers to see what the sample size n would be for this problem? Takes a lot of eyeballing. Yeah, absolutely. Good call. If you can identify the sample size, you probably have a good idea what's going on in the histogram. The way you can compute this is, well, just go from rectangle to rectangle. This is a category of people between that pH value to that pH value, 7.1. There's two of them here, five of them here, four, two again, and just one person. So tally those all up, and we get the overall sample size of 14. I'll delete this for the moment so that this diagram doesn't get too busy. It gets harder and harder for it to be useful if we put too much notation on. But that's the sample size in this problem. Well, let's take a look at the next content. Now that we're talking about histograms, the shape of the histogram does turn out to be really important. If it has the wrong shape, the statistical procedures of this book do not apply. The conclusions turn out just to be nonsensical information. So knowing when your data can use the statistical methods that we're going to describe in inferential statistics is just as important as the methods themselves. Histograms tend to be a really great way to visualize those data, to check conditions. And so we'll look at several histograms like this one down below, and then start describing what do we mean by multiple peaks, unimodal versus bimodal? What do we mean by symmetric? Or if it's not symmetric, what is a skewed histogram? Left skewed versus right skewed. So those are the things that we're going to take a look at coming next. All of these work better if we have a real context. So here's the next real bit of context. So this one's an interesting one because it refers to a nuclear meltdown in Japan in 2011. So the Fukushima reactor had a problem. It was over-engineered to be as safe as possible, but when a magnitude, I think it was somewhere in magnitude 9 earthquake hits, Doesn't matter how safe your engineering is, bad things happen. So all fail-safes broke. There was a meltdown in that reactor in Japan. And these kinds of meltdowns are really interesting to everybody because it actually affects everybody. The effects were felt across the ocean in the coast of California not too much later. So here's the story of this problem. This was always a fun one, but it's turning into old data already, 2025. I don't think we have a meltdown since, as far as I know officially. So it's nice that this is our latest problem on a meltdown. So here's the context. So first, a little bit of physics. Radioactive cesium, so these two isotopes specifically, is a waste product of nuclear reactors. Now, a study examined the radioactive cesium tissue concentration of a random sample of 15 Pacific bluefin tuna. They give us a scientific name, that's kind of nice. These were captured off the coast of California 4 months after the Fukushima nuclear reactor meltdown of 2011. And here are the findings for the radioactivity. So radioactive cesium tissue concentration. They tell us the units are becquerels per kilogram of dry tissue. That's a weird unit, but that's just how radioactive the fish was, how glowing it might have been in the dark, for example. When it says of dry tissue, this is what they really did. They have a random sample of 15 Pacific bluefin tuna. These are pretty big fish. And once they caught them, they put them in some kind of containment center. They're contaminated, right? No one wants to touch them. They dried them out. Then they ground them up, and then they just measured how much of the actual physical mass of this completely dried out, desiccated fish is in fact these two isotopes. So they made those measurements. Then they looked into the radioactivity of it, and these are the radioactive measurements of those fish. Units of becquerels per kilogram of dry tissue. So how much of it was cesium and how radioactive was the cesium? Again, complicated unit, but if you can imagine what happened to that fish, that's what went down. Honestly, the hardest thing about this whole description is the Pacific Ocean, even just in the locale off the coast of California, is a really big place. I'm not sure how they got a random sample. Not like they were pulling the fish, they were getting them off fishing boats, I'm assuming. So this is something that biologists would have to inform us to say, we know their migration patterns, and we know that these ones you did catch off the coast of California is well representative of all Pacific bluefin tuna. That's a big unknown in this kind of problem already. But here's what it looks like. Here's all the radioactivity measurements. And we're told further, historically, so we mean before the meltdown, radioactive cesium is naturally occurring, and the mean radioactive cesium tissue concentration in Pacific bluefin tuna has been below 2 becquerels per kilogram. That puts these numbers in context. The smallest one is 4.6. Biggest one is 15.6, and it's well above the average. Notice it said this word right here, mean. So once again, always think this as synonymous as average. So on average, that's what we expect radioactivity to be, less than 2 becquerels per kilogram. Every one of these fish is above average. So this is now giving us overwhelming evidence. Just in 4 months, we could detect the results for the nuclear meltdown waste entering into the Pacific Ocean. And that's really pretty shocking in a way, because again, the Pacific Ocean is a gigantic place. Just look at it on the globe. And the fact that they could detect this in just 4 months is almost creepy in a kind of way. Well, that's the whole study. This one's kind of a review problem so far, in parts both A and B, and then in part C, we'll look into the data, back on track, looking into the histogram. Hardest thing about this problem is, what is the population? The not as hard thing is, what is the sample? The reason the sample is not too hard to indicate is, it can be pretty brief when you go to describe it, and they literally said right here, there's a sample of 15 Pacific bluefin tuna. And those are the 15 measurements that are just listed out. So the sample size n is 15, and we can just say, for the sample, I'll do this one, the 15 fish caught. Or you just might have said the 15 fish used in the study, anything like that. You've described the sample to the fullest. You can give way more information, but you don't have to, because the sample always comes from the population. We're going to be more specific with the population, which clarifies what the sample really is. So let's think about this one. We might say, just to start off, and we'll poll the class on what else we need to add to be specific as necessary, but we might start saying it's Pacific bluefin tuna. You don't have to write down the scientific name. I'll just say, because it's a population, we're concerned with all Pacific bluefin tuna, but that's not the full story at all. There's a couple more things we need to add here. Anyone see what else we need to add to really nail down this population? Absolutely. The best things to think about are time and space. Where is it in geographically located? Because that's important. And if all of them were caught off the coast of California, we don't mean all Pacific bluefin tuna on the entire ocean. It has to be relative to where sample was really being selected. So that's highly important, necessary to describe the sample to its fullest. So let's say all Pacific bluefin tuna near the coast. I don't know why I capitalized that, near the coast of California. And still we need more. Anyone say what else we should say additionally? Exactly. We should say 4 months after the 2011 meltdown. We're really saying quite a lot, but it's all important, right? We don't care about all Pacific bluefin tuna off the coast of California in 2025. Those effects have diminished. We won't see the same radioactivity. It's probably below 2 becquerels per kilogram once again. We don't care before. We cared specifically after that event happened. That's the major part of the problem. So there's a temporal portion, what happened in time, and also a space portion, where is it happening geographically? Both of those are really critical to this population. So this one's kind of a tricky one. It would have been a tough exam question, I would say, without doing a lot of additional practice on these. So it's all Pacific bluefin tuna near the coast of California, 4 months after the 2011 meltdown. And you don't have to say the Fukushima nuclear reactor meltdown, because if you say 2011 meltdown, thankfully for mankind, everyone's going to know which one you're talking about. They're rare enough. Well, that's our population and sample. What we're really studying is just the 15 fish. If it was really random and it's really representative all at the same time, we know what's going on off the coast of California. Possibly the study was done just to see, are the fish even safe to eat? That might have been the big part of why the study was even conducted. But it was also possibly that biologists, ecologists, nuclear physicists, they're all just curious. Meltdowns don't happen a lot, so they're trying to learn as much as possible every time one does occur. Well, any questions, folks, before we go up to part B? Okay, part B is kind of a review of section 2.1 concepts. Pretty short one. It does say to explain, but I didn't say what level explanation, so you don't have to say much. Why is a bar chart not appropriate? Can anyone see why that's the case for this? We should not use a bar chart. It would be, yeah, it would be really long. Are you saying because there'd be a bar for 4.6, 6.9, and so on? Right. Exactly. That's the defect of this kind of data. We can't use the bar chart for these data. There'd be way too many categories. And so really fundamentally, the reason is these are quantitative data. So we really just default back to this table back up here. If it's quantitative, we should never use the bar chart. We should be using something like a histogram or even a dot plot, or later on we'll see a box plot. In the reading, there's a stem and leaf plot, but we're not going to do those ones in class. They're not as much value as you might think. So we're going to focus on the more practical things like histograms. So we might answer this one just by simply saying, since these data are quantitative, a bar chart should not be used. If this was an exam question and you're just saving time, you might have just said, it's because the data are quantitative. Or you might have just simply said, we should use a histogram because it's quantitative. Anything like that would have been just fine. But really, that's the major concept. Sometimes these are tricky problems because you have to wonder, what was the concept we're going at in the first place? And that's why if this does come out to be a similar exam question, it might be a similar quiz question as well, just so that you know something like that is coming up. Well, let's take a look at the data. It's really here, but like we've discussed, for any important statistical problem, it's not enough to just stare at data. I mean, we can see that all observations are above 2 becquerels per kilogram, but there's so much more going on there. We wonder, are there outliers? Where is the data accumulating? All sorts of interesting questions. How symmetric is the data? So those questions are resolved more better when we look into stuff like the histogram or the dot plot and so on. So it says below is a histogram that displays the distribution of these data. Let me blow that up just a little bit. Okay, that was too much. We can just drop it on the next page though. So here's the histogram of the data. All we want to do is summarize what the histogram shows. So we're just making some comments. A little bit more directed comments this time. It asks, does the data provide evidence that the mean cesium tissue concentration is larger than 2 becquerels per kilogram? So we're just summarizing, saying anything that you can see here that looks interesting, and answering the overall question. Anything that seems interesting to you all right out of the gate, just looking at this? Maybe one question is, do you all spot any outliers? No. I agree. It doesn't look like there's any outliers here. An outlier could manifest if maybe something like that goes on, and budget a little bit closer. If it looked like that, I'd say, yeah, we might have an outlier. But a piece of data like this would not be an outlier in this case. It's now too close. But things are even better. Everything is kind of right up next against everything else in terms of the data. But you know what? That's some interesting information as well. We might say there are no outliers. Maybe another thing we might say is, anyone spot how it's kind of weird that there is a big peak right here, and then another big peak right here at the same time? That's kind of interesting. Most of our data we've been looking at has one major peak. This one has two. So we'll later on call this bimodal data because there are two main peaks. You wouldn't necessarily use that word yet because we haven't defined it, but I mean, we're about to. This is our first look at real bimodal data, so we might as well say it here. 4 observations out of the 15 are between 6 and 8 becquerels per kilogram, and 5 observations are between 10 and 12. The data seems to be split up in a weird kind of way. Sometimes there's good explanations for that. Other times it's hard to say why. For biological data, it could be, I don't know enough about bluefin tuna, so anyone who might be more of an expert in that kind of thing can chime in at any point. But sometimes when it comes to biological data, it could be just the sexes. Maybe these are the males if they're bigger for this species. These are the females if they're smaller. Maybe the males just accumulated more cesium from just the way they migrate and feed and those kinds of things. Again, I don't know enough about biology to say for sure, but sometimes that's an explanation for bimodal data. Other times you have to look harder. It might be really hard to say why. So let's say here, there are two main peaks. One at, let me say, one between 6 and 8 becquerels per kilogram, and one between 10 and 12 becquerels per kilogram. Again, really pretty bizarre unit. We look into weird units in statistics, kind of par for the course. Aside from that, you could say a lot of other things. You could say the data ranges from 4 becquerels per kilogram up to 16. You might say the most typical value seems to be around 10 becquerels per kilogram. If you kind of glommed all the peaks together, everything seems to balance right at that point. Now all we have to do is make sure we address all the questions. Sometimes it's easy to just miss stuff on these kinds of problems. So let's go to this second part. What would you all say if you never looked at the data and you just saw this? Do we have strong evidence that the mean or average, let's mention that again, is above 2 becquerels? I would agree with you as well. The minimum here is at 4 becquerels. So if you're starting way out here, and that was just one fish in that range, everything else is way bigger, then yeah, we have great visual evidence just from this display in support of that statement. Let's just say, yes, this display supports that, the sample has more than 2 becquerels per kilogram, but what we're really trying to talk about is the population. So let's say it this way. This display supports that all Pacific bluefin in the population has higher than 2 becquerels per kilogram on average. So we have great support on that. If you didn't bring in the population, you didn't say all Pacific bluefin tuna, that's okay. I mean, we didn't directly ask you to bring in the population on this one. And notice I didn't even say everything about the population. It could have just said the fish in the population. That qualifies because your earlier work said what the population is. If some work already defined it, you don't have to keep repeating yourself in that kind of way, unless for specific problems, and we'll mention them when we get to them. So that could have been our full answer on this. And here's where statistics is kind of tough. People might ask you, well, how certain are you of that fact? We might have to do something further, like a confidence interval or a hypothesis test, to give a degree of certainty, because they're not talking about the individual values in the sample or the population. They're talking about the average of all fish in the coast of California 4 months after that meltdown in 2011. But really the big takeaway here is just to kind of review population versus sample and looking at a histogram once more to see what we can learn just from this display. Any questions at all, folks, with their end conclusions on this one? Okay, these are the main examples with actual context. What we're going to do now with the next part of the notes is just look into more about histograms. So here's that next part of the notes. There's a lot of terminology that goes along with all this, so that's why we've been kind of hinting at it all along, so that we can kind of start getting it in our head before we throw all this vocabulary at ourselves. But this is the last part of the notes. All these things in bold are important bits of terminology we should be familiar with. The white spaces, we're just going to draw our own histograms. You might be asked to do that on an exam as well. You might be asked, draw a histogram that's skewed to the right. It's really just a concept check if you know what that looks like. So if that's a potential exam question, we're also doing it here on the notes as well. It says, histogram is said to be unimodal if it has a single peak, bimodal if it has two peaks, multimodal for more than two peaks. I actually don't have a lot of data like that in this specific class, but it could come up occasionally, possibly in the reading, for example. So it's here in the notes as well. So for just quick examples, here's my example for a unimodal. What I'm going to do in all these examples is just kind of duplicate the sketches we have below. There'll be a horizontal axis for the quantitative variable, but I have no context, so I won't say anything down below here. I'll just sketch a random histogram. So this is what unimodal data could look like. This one seems to taper off to the right. Maybe a little bit more tapering off to the left. Let's make one come up just a little bit and then come back down. So this one is unimodal because it has just one single peak. What I mean by that is, even if it comes up just a little bit, this is not enough to tell us that's bimodal data. It's got to be just a little bit more extreme than that. If it was a little bit higher, we might start to wonder. If it's noticeably higher that it just catches your eye, you're looking at bimodal data. Again, it's all subjective, qualitative descriptions. It's just things that we have to get used to seeing. Practice here on the notes, practice in the homework on MyStatsLab helps out quite a lot with this kind of stuff. Let's look at bimodal next. I want to make it similar to this one, but make this one just a little bit more extreme so now it just really looks like bimodal data. Or take a mental image of what's here and just take a peek at this one. We might consider this one bimodal as well, like we said, because this is a main peak, and this one is a main peak as well. So bimodal could look something about like this. Here is one massive aggregation of data right there. I'm try to make my rectangles look a little bit better than that. When you draw a lot of these, it's easy to kind of get a little lazy and they look a little bit broken or wonky. But that's okay. You don't have to have the perfect steady hand on the notes or anything if you do this as an exam question. So trying to copy the shape to the left, but this time, let me make it come up maybe just like this. Suddenly, something happened over here. Data accumulated majorly in this location on the quantitative variable, but it started to accumulate here at the same exact time. Now we're starting to look at bimodal data, and I mean, just the more extreme this gets, the more it's definitely bimodal. So this one's just a dead giveaway at this point, kind of like our prior data. Or this one is maybe a bit of a judgment call. So let's make it seem slightly less like a judgment call for our individual answer. When I do give an actual real exam question or a quiz problem, I try not to put it in that middle ground where you could have gone one way or another. I try to make it obvious that this one was just a tiny blip, not actual bimodal data. This one is something definitely going on. I try not to give those middle ground type of problems. So this one's bimodal because now it has two peaks. And the more peaks we put on there, we might call it trimodal. At that point, we'll just call it multimodal if there's 4 peaks, 5 peaks, and so on. But any questions at all, folks, for these kinds of data? Okay, you know what's hard is coming up with context where these things come up. I did mention, like, if you're talking about ecology, sometimes different species sexes can give you different things. But let's put down one interesting example with context just to get a feel for this. So this is, let's say, number of gallons of gas pumped. Ran out of space there. At a gas station. So now this is multimodal data almost for sure. So you're not necessarily going to be someone who's like a district manager of Maverick, but you can imagine people pull up to your favorite gas station, and sometimes if it's like Thursday, you get paid on Friday, you might be someone who's pumping between 0 and 1 gallons. You're just topping off so you can get to work on Friday. So there could be a lot of people out here. Then 2 gallons. You know what? This scale is going to cause me some trouble. Let me try to fix this. Let's call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Probably more gallons in your car already, but you know, there's other vehicles out there. 25, 26, 27, 28, 29, 30. I wanted to go a little bit further, but I think we kind of get the idea. There could be semis pulling up, pumping like 80 gallons of gas or something like that. So maybe this is not fully realistic, but let's not take too much time on this one. The data might start looking like this. Maybe that's kind of extreme. I don't want this to seem like a dystopian future, but lots of people pumping between $0 and $1, topping off. Maybe some people in these different ranges. These people are kind of topping off as well. Then maybe a little bit of a gap there. Then a lot of people like to just pump $10 or get somewhere around there, and they call that good. So something like that. Some people might be going to right where their low fuel light indicator just pops up, and then they fill up their car, and maybe they're around 15 gallons. So it could look like that. And now we're looking into some cars that just have more capacity. Maybe some people have trucks and they're filling up, like we mentioned, and it could look something like this. I don't know the average amount of gallons a typical truck holds anymore these days. So this would be just a random example for something that is now multimodal. Maybe not the most realistic graph, but kind of believable in a way for how people's pumping behavior at a gas for how much they fill up their tank would really actually look like in real life. There'd be lots of different main peaks, main aggregations of data. Well, any questions about that so far? Okay, we're always interested in these main peaks because we want to know the average or central value. Unimodal data is easy. Our average is going to be sometimes right around where the main peak is. It gets trickier when we're discussing bimodal or multimodal data. In this number of gallons of gas pumped, maybe we do need to separate people by car types or their situation, their paycheck to paycheck and not getting paid yet, those kinds of things. So next category of things we'll study with our histograms is symmetry versus non-symmetry. This will be the last part of class since I don't think we have enough time to crack open the section 2.3 notes, but we're getting pretty close to being into section 2.4 when we come back on Tuesday using that TID4 like we mentioned. So now symmetric data is like the gold standard of nice data. It's easy to handle. Your statistical conclusions are going to be very strong. There will be no worries that they didn't meet the requirements. And here's what it's going to look like. It says your histogram is symmetric. There's a vertical line of symmetry that you could place so the left-hand side is a mirror of the right-hand side. So let's draw something that seems to fit that description. It doesn't have to be unimodal, but this is often the symmetric data that we study in this class, one main peak. The data after the main peak starts to fall on the left and the right in kind of a predictable way on both sides. Notice this doesn't have perfect symmetry. This height is a little bit higher than the one to the left. This height, 2 squares off, rectangles rather off, is a little bit higher than the one over here. But that's okay. The important reminder about data is that real world data is almost never perfectly symmetric. If someone did a really large governmental study and the data was perfectly symmetric, you might start to wonder if they fake the data at that point, because real world data is often pretty messy, has imperfections on symmetry. This one's not perfect by any means. Notice there's more data on the right than there even is on the left. I have 4 rectangles off the main peak versus 3 here. But if you put a dashed line on this, printed this out and folded the paper, the heights would roughly line up in this kind of way. Not perfect, right? My arrowheads are rather the height of where those were. This has nothing to go along with it whatsoever, but that's okay. This would still be considered very, very symmetric data. Let's emphasize this. Highly symmetric. Actually, let's leave that dashed line just to convey the thought. There's a vertical line of symmetry such that the other side is roughly a mirror image of the other. Your data is highly symmetric. So these are the data everyone likes to see. If you know that you're going into, say, a biology program and you might do some research, you're probably going to produce your own data. And if this is what your data looks like, you might celebrate on that with that, because your statistical analysis is going to be a lot easier than it could have been for the skewed cases coming up. So skewed data is problematic, and data gets skewed in a lot of different kinds of ways. And at the same time, there's 2 directions of skew. We already looked at skewed data once. Let's take a peek at it again. These data were skewed. We have aggregation here, and then stuff trails off to the right, and the outlier kind of contributed to the skew as well. Data is trailing off to the right. We'll call that right skew or positively skewed. Let's draw our own versions of this using actual histograms, since that's what we're most likely going to see. This might deserve a new page as well. So first definition is not symmetric means skewed. So this has slight skew, but it's mostly symmetric. In fact, highly symmetric is a better way to say it. We mean pictures that get way worse than that, where there's obviously just no symmetry whatsoever. It looks broken in a certain sense. We'll look at 2 different kinds. First, we'll look into right skewed data. You could call this positively skewed, but I think most people just say right skewed. It's faster to write, takes less oxygen to say, and it's a quick way to say it. Likewise, negatively skewed, I'll often say just left skewed as well. So first, here's the right skewed data. Let's make this pretty extreme. It has 1 main peak. It could be bimodal, but let's focus on just a unimodal description first. It'll be more common. Then data falls rapidly in this kind of way. There might be an extreme outlier out here, a major, major extreme outlier out here. We'll actually look at real data that actually fits this picture. And this is right skewed. Nothing even close to being symmetric about these data whatsoever. In fact, these are both here and here extreme outlier. Actually, let me say that slightly differently. I'd say this one is just more of an ordinary outlier. It's pretty far. This one's the majorly far one. So this one is an outlier. This one's an extreme outlier. Nothing over here is an outlier, even if we put in another observation pretty close by. It's still by the main pack of data. But this is what right skew data would look like. Right skew data usually comes in when we're looking into survival times. Survival doesn't mean we're doing some weird animal experiment necessarily. These could be someone's testing out a new LED light bulb, and this could be hours of runtime. So most light bulbs might stop working after, say, 10,000 hours. I think that might be reasonable for LED, maybe a little high there. But when you manufacture batches of things and just see how long they run, sometimes the mega survivors show up, the light bulbs that just never quit working until a really, really long time. So survival data typically looks something like this. Let's say, just to add context, number of hours a light bulb runs before breaking. So that would be a typical kind of context for that. There's something weird about data. The more you look at it, it's a lot easier to come up with an example of right skew data than it is for left skew data. That's pretty weird. In fact, our multimodal display actually looks like kind of symmetry to this in a sense. I take that back. But let's do left skewed nonetheless, because it can come up. So left skew data could look like this. There could be observations to the right. I made a main peak and then everything was to the right of it, but it could look a little bit more like this. Then just stops right around here and then starts to fall to the left as well. At this stage, this looks symmetric. So let's break it. Let's make it left skewed. The more and more data that keep piling on, going off to the left, contributes to the skew that's going to the left on this one. So this one's pretty left skewed as well. No apparent outliers on this one. And can anyone think of a context where left skew data might realistically show up? This is actually really hard to think about, to be honest. I personally have just one good go-to example. I don't have a second one. I would have to think about it to come up with a second good example of left skew data. So this is my personal go-to example for when data actually shows up left skewed regularly. Let's put 100 here, percent. Let's put 0% out here. And let's say this is a hard physics exam. Physics scare me, so that's something I would usually say if I'm talking about a hard exam. Maybe this is at the 50%. And this is a nice picture. Not everyone did well. Physics is tough, right? This is around the 70% region. So the class didn't do too bad if we're looking at that. The average is somewhere a little bit more to the left because of the skew. But exams, because there's a cutoff right at 100%, or maybe if there's extra credit, that could be higher. Maybe we should call it a percentage though, if it's higher than 100. But there's an upper cutoff. Everyone tends to do pretty well. But if it's tough, people start to skew off to the left. So how do we identify right skew? Right skew means trailing off to the right. Where is the tail of the data? Or where is it trailing off? And left skew data just means right here, it's trailing off to the left. So that's what we mean by skew. Both of these data sets are going to be really, really problematic. This one is going to be the toughest of all because the extreme outlier and the outlier makes the statistical analysis tough, but not impossible. There's all sorts of things we can do, all sorts of ways to re-express and try to fix the data, clean it up. It just means though, if you're doing a capstone project, maybe you're an economics student, maybe you're a nursing student, and you go to gather data, if your data looks like this, contact the statistics department at ISU and they'll help you work this out. They are people all over on staff, PhD statisticians, who just love seeing this data. And undergraduate students, graduate students are always welcome to visit and work with them. You are probably going to be encouraged to do so by your own department as well. But any last questions at all, folks, with looking at these shapes of data? Okay, well, that would be our stopping point for this week. I think we mentioned before, one of the things that I do on this Canvas page is we didn't get to 2.3. That's really here just in case. Maybe we went really fast for some reason. I try to make these sections available so you kind of know what's coming up next as well. I'm always gonna move them around so they land where we're gonna complete them up next week. So if things look slightly different, that's gonna be the reason why. But have a great weekend, folks. We'll return to section 2.3 on next Monday. Take care. Sure.
Then, could you remind me where I could go take extra practice?
Oh, yeah. So that's gonna be directly at the e-text. And these are just the problems that are at the end of the chapter.
So,
So you go to say like chapter 2, working in that one. And sorry, it's weird waiting for your textbook to load up. Then click on that link there. And then pop out the index on this one. Go to the, let's say you pop or click on the arrow on that 2.2. And then, let's see, oh, I'm incorrect on that. It's at the very end of the chapter on the exercises right there.
oh, okay,
Yeah, so that's where the book exercises are.
Yeah.
But you know, if you're curious about doing maybe more similar exercises like in the MyStats lab, I could look into a way of just adding more exercises just for the sake of practice, if that'd be helpful.
would like Khan Academy be?
That'd be a great resource as well,
Okay,
yeah. Same kind of content, slightly different take, but you're doing the same sort of stuff. That'd be a great way to practice.
Okay,
Like I mentioned before, when I get closer to this week here on exam 1,
Yeah.
I might try to post this early if you wanting to get additional practice. But I'll be posting a kind of a big like packet PDF that are similar to these problems, like this kind of stuff here, except it's all blank. And those are just additional problems to practice. They'll be highly similar to real exam questions as well.
sweet. Yeah, I just wanna, like, almost every weekend, whenever I'm not busy, I like to go over every like lesson that I have. in my
Awesome, yeah.
classes, And then just like remember like, okay, I was in that class, and we went over that lesson about the quantitative variables, and just like right now I know more about what we just learned, which is the first lesson that we did.
Yeah, that's awesome. It's
So-
all just kind of building into each other, right?
Yeah, so I just start off with what we did the latest, and then later go back to what we started, and then just go like follow up until where we left off. And then
Cool.
Just like it sort of sits there, and I finally like remember it without having to really try.
Yeah,
So that's just like second nature, really.
that's awesome. Yeah, each time you're doing that, you're just reinforcing it, keeping it up there. And yeah, probably what I will do is actually post those review problems a little bit early. You'll see them under here on exam 1. I'll just say sample exam 1 problems, early draft. So if you want to see just another set of problems, these ones are a little bit more similar to real exam problems than even the ones in the book. They'll be another extra resource. I should make a reminder of that now that I said it. I have a bad habit of saying I'll do something and then just totally forgetting.
Yeah, I feel the same way. You gone to the fair yet?
Not just yet.
Are you planning on going?
You know, honestly, I might skip it this year. It's kind of a busy year for me. Sometimes I'm just like every other year I decide to go. How about you? Have you been there yourself?
Yeah, when I was like a freshman, sophomore in high school, but, yeah, it's been a while.
Yeah,
I'll have to text some friends and.
it's still the same place. It's like exactly the way you remember it, which is weird. Same exact fairgrounds and everything is in the same spot. It never seems to change. The only thing that changes is there's just more people now.
Really crazy how Idaho's growing at pretty fast pace, really.
Yeah, it's bizarre. I lived here my whole life, and so I've seen some crazy changes for sure. I read an article not too long ago that we have the same police force, essentially, the same amount of staff as we did in 1990, but we've got, I don't remember the exact figure, but like 20,000 extra people. So the police are working really hard. I wish they would get a new budget.
Hey, that's awesome.